One of the problems facing geologists today is the fossilized tree. There are a number of examples in Australia and America and elsewhere where a fossilized tree can be seen running vertically through a number of coal seams. Here's an example from the coalfields of Birmingham in Alabama in the United States. Some of these fossilized trees, 12 meters or more in height, can be seen running through a number of banks. This model gives some idea of the situation. Now, the curious thing is that we are told that any one of these banks takes millions of years to form. Now, if this was the case, it would take millions of years to bury the tree. But that's not possible, because the tree would decompose or rot long before it was all buried. So, what is the explanation? Well, a scientist has studied the problem, and the episode you're about to see will give you an idea of the implications of his startling but exciting discovery. Now, in order to understand the explanation, it's important to know the difference between a layer and a bank. These are banks, these areas coloured orange and yellow and bluish. In each bank, you can see a number of strata. What you can't see are the layers. You can't see them because as each layer of sediment arrived, it sorted itself out into the banks that you can see. If you could see them, they would look something like this. After you've seen the film, you will understand why knowing the difference between a bank and a layer is so important. It not only provides the key to the fossil tree problem, but it also explains why the theory of evolution is crumbling. And what's so important about those rocks? Well, they're not any old rocks. They are made mostly of tiny grains of sediment. They are called sedimentary rocks and cover 3/4 of all the land on Earth. And what's more, they were formed under the sea. When the sea level dropped and the sediments were exposed to the air, they dried out to become rocks.
Look at this cliff face. It's divided into facies, sometimes called banks or deposits. The sandstone deposit has been coloured yellow, the deposit of clay blue, and the limestone coloured orange. Each deposit or bank is subdivided into strata. These horizontal lines are strata. To understand the incredible story that this film has to tell, a closer look at the strata in the deposit is necessary. They follow a pattern. The larger particles collect together in a line at the bottom, then the smaller ones gather on top. This pattern is repeated throughout the deposit. Sometimes a break or joint can be seen between the top strata in one deposit and the bottom strata in the deposit on top. These breaks are called stratification joints or bedding plane partings.
For some time now, there's been a suspicion that these rocks contain a secret, which when discovered will change our ideas on the most important subject of all. How did mankind originate?
One of the first sedimentary rock experts was a German. His name was Johannes Walter. Whilst in Italy at the end of the last century, he examined the sediments in the Bay of Naples. He discovered, by boring vertically downwards through the sediments in the bay, that the banks that lay on top of each other were in the same sequence as those that were lying next to each other horizontally. The sequence of banks that could be seen lying side by side as he went from the coast out to the sea was the same as the sequence of banks that lay on top of each other in a downwards direction. He realized that the belief that the bank at the bottom was older than the one on top was wrong. Quite obviously, all the banks, the one at the top, the one underneath, and the one at the bottom were all still forming. They were forming sideways, so that part of the top bank was the same age as part of the bottom bank.
It didn't take Walter very long to work out what caused the banks to form sideways.
The particles of sediment coming into the sea from rivers, floods, and wind sort themselves according to their size. These larger particles, coloured yellow, stay near to the coast. The less heavy ones, coloured blue, are washed out a little farther. Then the tiny sediments, the orange ones, are carried out by the waves and currents even farther. It can be seen that the layers of new sediment are deposited side by side. The particles of sediment in the layers sort themselves out according to their size into the banks of various types of sediment. This could be a bank of pebbles, this a bank of sandstone, and this one clay. So the banks form sideways. That part of the bank nearest the coast is older than the part of the same bank farther away from the coast. So this part of the bank at the bottom is the same age as this part of the bank at the top.
Before Johannes Walter, in 1870, two Russians, Golofkinsky and Inolstrantsiev, had noticed that in ancient ocean basins that had filled up with sediment, the same series of deposits could be seen on the surface side by side and vertically, one underneath the other. The feature of these series of deposits or facies are that they are parallel to the basin slope. Those in the Gulf of Naples, observed by Walter, are not. They are almost horizontal. The reason is that apart from small changes caused by the tides, the series of deposits in the Gulf of Naples and elsewhere result from the sea always being at the same level. The position of deposits of sediments in ocean basins, such as those observed by the two Russian scientists, would seem to be the result of major changes in the level of the ocean. Rising water level is called a transgression. Falling water level is called a regression. When the water rises or transgresses, perhaps as the result of tidal waves, the sediments deposit parallel to the sloping sides of the ocean basin. The larger yellow particles depositing next to the slope. When the water level falls or regresses, the sediments deposit with the smallest particles, coloured orange, next to the slope. Looking at former ocean basins, now filled in with sediments, the position of the deposits or facies indicate that the waters of the past must have risen and fallen time after time in fast succession. As sedimentologists would say, transgressions followed by regressions seem to have occurred in cycles. The different kinds of deposit are again the result of sediment sorting itself out sideways, and not one type of deposit superposing itself upon another. It would appear, therefore, that the origin of sedimentary basins is the result of cycles of fast, rising and falling water levels, or more technically, transgressions and regressions. The position of the deposits is not, therefore, the result of the principles of superposition and continuity, but the application of the law of Johannes Walter. These cycles of rising and falling water levels couldn't have taken place all around the world at the same time. Perhaps they were like large-scale ocean tides, so that where the water level was rising and depositing massive sediments in one place, at the same time sediments were being deposited elsewhere, where the water level was dropping. The reaction of the other rock experts was that Johannes Walter's discovery only explained coastal rocks, and that deep-sea sediments were always formed by a layer of sediment forming on top of another, and that the layer on top is always younger than the layer underneath. In this cliff face, probably formed from deep-sea sediments, the strata in the banks at the bottom are believed to be much older than the strata up there in the top. The reason for this is that geologists believe that strata and layers are the same thing.
In the 1970s and 80s, several holes bored into the bottom of the Pacific Ocean by the Glomar Challenger vessel produced samples of sediment that showed Walter's discovery applied to the deep-sea sediments just as well as coastal sediments. This meant that virtually all sedimentary rock formations in the world must have been formed in the same way.
So what does all this mean? Well, take what is considered to be the biggest, the widest, the deepest, the longest canyon in the world, the Grand Canyon in the United States. The sides of the canyon display banks, one on top of the other, from the bottom of the mile-deep canyon to the top. Each bank is said to indicate an age in geological time. Yet, what we know from Johannes Walter's discovery and the Glomar Challenger deep-sea borings indicates that parts of different banks could be the same age. Nevertheless, there were still those who found this difficult to accept. But two recent events have occurred, however, which should remove all further doubts.
In 1980, Mount St. Helens, a volcano in the United States, exploded. It flattened an extensive forest and caused a tidal wave in a large local lake. Within hours, 600 feet of sediment had formed, which dried into rocks complete with strata. As a result of the explosion, huge amounts of mud flowed through the adjacent rocks and bored a canyon over 100 feet deep and 200 feet wide.
Now, it has always been believed that strata in rocks and canyons take millions of years to form. But both these geological formations were formed within several hours.
The other event took place in a laboratory. French sedimentologist Guy Berthaud discovered two immensely important facts. The first was that sand, flowing continuously, whether in a vacuum, in the air, or in the water, sorts itself out into alternating deposits of large and small particles that look like layers but are not layers. The second vital fact emerged during the program of experiments he was directing with the State University of Colorado. Looking through the transparent sides of a large tank or flume, he studied the particles of sediment in the moving water. He observed that when the speed of the current was reduced, only the large particles of sediment were deposited. When the current was increased, microstrata started to form. So the grading of particles in strata was not just the result of layers of sediment piling up on top of each other, as had always been thought. The grading could simply be due to variations in the speed of the current when the particles were deposited. A further startling discovery was that joints or breaks between strata are the result of desiccation or drying out of sediment. It used to be thought that these joints were caused by an interruption in the supply of sediment. It was thought that the surface of the last deposited strata had hardened, and that many years later, new sediments started to fall, and a new strata formed on top of the old one. This theory now has to be abandoned because of two new discoveries. The first was that the underwater borings of Glomar Challenger showed that surface sediments under the sea never harden. In fact, hardening of sediments only starts 300 meters below the seabed. The only known exception is chert sediments, which even so only start hardening 100 meters below the sea bottom. The second discovery was in the laboratory. It was found that when the sea level drops and the damp sediments are exposed to the air, breaks occur between some of the strata as part of the drying out process. So these joints or breaks have nothing to do with time. These experiments, performed by a team of experts over many months under the most rigorous laboratory conditions, have been filmed and are available for all to see. They confirm the most important fact ever discovered in the history of sedimentology. Strata provide no indication of age. Ghiberto has shown that the strata you see in these banks are caused by changes in water currents. They don't just deposit themselves one upon the other over vast periods of time. They form sideways in a crab-like fashion, just like the banks.
These experiments were then performed on a larger scale and presented to the 14th International Congress of Sedimentology in the following documentary film. Sedimentary rocks are fascinating because they witnessed the past history of the Earth. Their study should unveil mysteries about their formation and the history of living species. The principal features of sedimentary rocks include distinct stratas of relatively homogeneous material. Intermittent settling over very long periods of time figure among possible explanations of stratification. Internally, sedimentary rocks display microscale stratification or lamination of relatively coarse and fine particles. Because sedimentary rocks form from settling of particles underwater, it is instructive to study fundamental sedimentation patterns in the hydraulics laboratory. A mixture resulting from equal weights of coarse sands in black and fine sands in white is tested in the laboratory.
Consider the motion of a sphere rolling on a horizontal surface. The radius of the sphere is r, the mass is m, the angular velocity omega, and the translation velocity v is equal to omega times r. The moment of inertia of the sphere is equal to 2/5 of the product of the mass m and the square of the radius. The kinetic energy of the motion is given by the following formula. E is equal to 7/10 of the product of the mass times the square of the velocity. This formula shows that at a given velocity, the kinetic energy of a sphere increases with the mass. It shows that coarse particles have a higher kinetic energy than finer particles.
This example illustrates that rolling coarse particles have more kinetic energy than small particles. The mobility of coarse particles in front of obstacles or surface perturbation therefore increases.
Consider a homogeneous mixture of coarse particles in black and small particles in between. When we set this mixture into motion, the small particles, which have a lower kinetic energy, fall between the coarse particles and deposit on the bottom of the moving layer. The coarse particles with higher kinetic energy roll on top of the fine bed of fine particles.
Particle segregation occurs under lateral motion of a mixture. Coarse black particles roll on top of fine particles when they have the same specific gravity.
Submerged particles under hydraulic shear stress also display the same particle segregation characteristics. The fundamental question about lamination is the following. Does nature produce repetitive segregation under a continuous supply of sediment? First, the submerged conditions are examined. The turbulent fluid motion surrounding the particles led scientists to believe that lamination was caused by periodic cycles of turbulence. When the same experiment is carried out in the air, the settling cone displays all the features of lamination through repetitive segregation. Moreover, the laminae thickness increases with the feeding rate of the sediment mixture. It should be noted that laminae form in the direction of motion, here at an angle exceeding 30 degrees. Given the absolute vacuum is at minus 29.92 inches of mercury, the hypothesis of turbulence is tested near complete vacuum at minus 22 inches of mercury. Lamination develops without the presence of a surrounding fluid. Lamination therefore depends on the mechanical interaction between particles of different sizes, different shapes, and different densities. Under submerged conditions, lamination also occurs during gradual aggradation of the bed under plain bed conditions. Here's the same lamination sequence in accelerated motion. Large-scale experiments on stratification were carried out at the hydraulics laboratory of the Colorado State University Engineering Research Center. For the experiments, a 4-foot wide flume measuring 60 foot long recirculates 1,000 cubic feet of water and 8 tons of a sand mixture. This flume provides a continuous supply of coarse and fine sand particles under steady discharge conditions.
Consider a typical delta sketched on the board. At the initial time T1, the delta is comprised of 3 parts: the top set, the foreset, and the bottom set slope at initial time T1. Over time, the coarse particles rolling on the bed slide down the foreset slope of the delta and accumulate as the delta progresses in the downstream direction. Finer particles rolling on the bed settle and form a layer of primarily fine particles. The particles in suspension are carried through and deposit on the bottom set slope of the delta. After a certain time interval, we get a second bed profile at time T2. The sediments accumulated on the bed from time T1 to T2 define what is called a layer of sediment. A layer of sediment is the accumulation of sediment between the initial time T1 and the subsequent time T2.
This typical delta gradually progresses in the downstream direction A close look at the top set slope in slow motion clearly shows a laminated deposit of finer particles. The thickness of the top set deposit decreases in the downstream direction as the foreset slope of the delta is approached.
Over a long period of time, the accumulation of sediments displays clear stratification, with fine particles on top, coarse particles in the middle, and fine particles on the bottom. It is important to understand that the chronology of the formation of the deposits depends on the layers and not on the strata.
Isochrones correspond to the interface between successive layers, not strata. The thickness of strata is determined by the changes in sediment transport that occur in non-uniform flow.
Let's now consider two particles in the delta. Particle A in the upper strata and particle B in the lower strata. Particle A deposited at a time T1 before particle B. Particle B in the lower strata therefore deposited after particle A in the upper strata.
Increasing the flow depth while keeping the discharge and the supply of sediment unchanged results in more complex sedimentary features. Substantial deposits accumulate with features including deltas, dunes, and ripples at various stages of development. A dried delta, viewed from the flume sidewalls, displays clear stratification characteristics in terms of superposition of deposits with similar particle size distribution. A cross-section is cut through the delta to examine the primary features of deposits of sediment mixtures carried out under steady flow and a continuous sediment supply. The cross-section displays a clear superposition of strata of fine particles in white and coarse particles in black with clear lamination.
Looking at the cross-section of superposed strata, it is tempting to conclude that the strata correspond to successive sedimentary layers, that they result from discontinuous sedimentary periods, that each strata is younger than the one underneath it and older than the one above it, and that all points of the same strata have the same age.
The stratification experiment invalidates these hypotheses because these strata are not identical to successive layers. Moreover, clear stratification is observed under a continuous supply of heterogeneous sand particles.
Why is this important? Well, quite simply, because strata have been used to date sedimentary rocks and the fossils in them for over 100 years. And now, for the first time ever, there is experimental proof to show how strata form. And it is quite obvious that strata cannot be used to date either fossils or rocks. In fact, the fossils in the bottom strata could be younger than the fossils in the top strata.
Here you see some sea creatures which live at different ecological levels. A heavy influx of sediment arrives and they all get buried. Eventually, if no air gets to them, they could turn into fossils. Obviously, those buried in the top strata are the same age as those in the bottom strata, as they were buried in the same layer of sediment. Then another heavy layer of sediment arrives, and more sea creatures are trapped. But what is more important is the ones at the top of the previous layer were buried before the one in the bottom of the last layer. So the one at the top here is older than the one at the bottom.
Let the director of the research program explain.
La théorie de l'évolution se base sur la
Evolution theory is based upon the belief that a succession of fossil species in a scale of geological time demonstrates that evolutionary progress has taken place. As we have seen, however, and as we have shown in the laboratory, layers of incoming sediment have been wrongly identified as being strata. The scale of geological time and the chronological succession of fossils have been calculated on this mistaken belief that strata are successive layers of sediment. A single layer of sediment can sort itself out into parts of many strata. So the position of fossils in the rock strata could simply indicate the ecological zones of marine species. Stratigraphy, as interpreted by observable facts and experimental data, challenges the geological timescale and therefore evolution theory.